Okay, so for two-slit interference, we have this situation where you got your two slits and they go off at some angle, right? And there's a path difference here. That path difference is d sine theta, right? And that's equal to your condition. Whether that's constructive or destructive interference, we don't know. What we're going to do in this case is we're told that okay, so the center of the pattern is over here somewhere, and then we're off somewhere above the pattern, some distance y1, or I'm just going to call it y because I don't know what y it is. And we're told that y is equal to 12 millimeters. And this distance, L, is 3 meters. Okay, so, alright, so this angle theta that this light goes off at, we can say that that's dy over L. That's going to equal our condition. I'm going to set the condition equal to m lambda. And I'm going to solve for m. Here's my thinking, right? So I know d, I know y, I know L, and I know lambda. If I could solve for m, let's say that m works out to be a half. Well, that means that the path difference was half a wavelength, and we end up right here at the first maximum, or the first minimum. What if I solve for m and m equals 1? Well, that would mean that we're right here at the first maximum. What if I solve for m and m equals 1.5, 2, 2.5, 3, and so on? So I'm going to solve for m and see if that tells me. Now, if I get an m that's not exactly, 1 or 1.5 or 2 or 2.5, then that means we're somewhere in between. All right, so m is equal to dy over L lambda. Okay, now I'm told the slits are separated by 0.4 millimeters. Y is 12 millimeters. And then L is 3 meters. And the wavelength is 643 nanometers. That works out to be 2.5. Okay? So that means the phase difference, the phase shift, or the path difference, right? This path difference right up here, sometimes we call that little delta. The path difference is 2.5 waves. So that means it's a dark fringe.